There are two classic problems that are solved based on limits. It's these two major problems that really brought calculus about. The first is known as the tangent line problem. And the second is known as the area problem. Now, here's a basic idea of the tangent line problem. I have a set of axes here, x and y axes, and I have some curve, some function, f of x. I guess we could say y equals f of x. And at some point, say c, so when x equals c, I'm right here on the curve. Now, the question is, what's the equation of the line tangent? Well, I know it's going to have the form y equals mx plus b, but what's the value of x and b so that it is in fact tangent to this curve at this specific point? Well, that's much easier said than done. Probably the best way to think about this is if we think about the idea of a position function, and the change in position is velocity. So if we start talking about the idea of average velocity versus instantaneous velocity, we might be able to get a slightly better picture of what this is all about. So let's take a look at the idea of average versus instantaneous velocity. Now I'm going to have a position function, s of t. And let's just say that we know that this position function is going to be s of t equals negative 16 t squared plus 100 t. And this 100 here, you might recognize this because you've seen it probably a zillion times in algebra and pre-calculus. This is actually the initial velocity. So very commonly we use this as v sub I, initial velocity. And also let's just say that our velocity here is in fact in feet per second. Okay, so this curve is going to look something like this. When t is 0, I'm at 0. It's going to go up and come right back down. And you can actually very easily figure out what these intercepts are using algebra type techniques. So here's the t-axis and here's the position function, or the y-axis, s of t. So let's just say 1 second after launch, because what this is saying is I'm going to launch something at 100 feet per second from ground level. And how high is it at different times? Well, here's at 1 second, here's 2 seconds, and I'm just estimating. I don't know what this really is, where the vertex is. I'm not sure if that's at 3 or 4 or 5. So I don't know where that really is. You can figure it out, but that's not the point here. So at 1 second, it's roughly here. At 2 seconds, it's roughly there. So if I draw a line between these 2 points, I could easily figure out what the slope of this line is. This is not the tangent line, but I could figure out what the slope of this line is. Now, if this is seconds, 1 second and 2 seconds, then obviously there's 1 second transpired between them because 2 minus 1 is 1. So if I take the change in position, this distance from here to here, up and down, and I subtract those, I find out how much or how far the thing's traveled vertically, and divide it by the time that it took to travel it, then that's going to give me the average velocity. So let's just say velocity average, AVE, use a subscript like that, is going to actually equal the slope, m. This line is referred to as a secant line. A secant line will connect a curve at 2 points. So I'm going to say m sub SEC. So this is the slope of the secant line. Well, this is going to be equal to s of 2, the value at 2 seconds, minus s of 1, the value at 1 second. That's going to give me this piece right here, delta S. Divide this by, in this case, 2 minus 1, which will give me this piece right here, which is delta T. So this is really delta S over delta T, which you'd recognize this is the exact same thing you see all the time as delta Y over delta X, which equals the slope of a line when we use Y and X rather than S and T. So if I actually put this into calculator and do this, what I'll end up with is a 136 minus 84 divided by 1, which will give me 52. So this is saying the average velocity is 52, and we're dealing with feet per second. So I launched this thing at 100 feet per second, and the average velocity between 1 and 2 seconds later is 52 feet per second. Well, obviously it's slowing down because gravity's pulling on the thing. Now, all of this is fine and dandy, but this is not the whole point. The point is, I want to know what the instantaneous velocity is, not the average. The average velocity, we did nothing here other than using algebra for. Where we need calculus is to figure out what the instantaneous velocity is. What is the velocity, the actual velocity, when I'm not at between 1 and 2 seconds, but what's the velocity when I'm actually at 1 second? What is it at this point? Well, if I take this value of t and start moving it that way, so maybe I'm going to be at 1.5 seconds, I can do the exact same thing. I can calculate the slope of that secant line. Well, what if I take it and move it even closer? I get closer and closer and closer to 1. So at some point, I am so close to 1, actually I'm infinitely close to 1. I'm not at 1, but I'm infinitely close to 1. Well, the secant line is going to become the tangent line. So if I just start taking values, this value here of 2, and start making it smaller, 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 making it closer and closer to 1, and putting it into this little equation here, then I'm going to get estimates, closer and closer and closer estimates to what this instantaneous velocity must be right there. So let's take a look at, let's make a little chart here. I'm going to say here's a time interval. And this is the average velocity. So my time interval is going to be on 1 to 2 seconds, which we just did, and we got 52 feet per second. Now I want to take a look at the average between 1 and 1.5 seconds. I need to figure that out. Then maybe 1 and 1.1 seconds. I need to figure that out. Then perhaps 1 and to 1 point, let's stick some zeros in here, 0.0001 second. So you see this interval right here is getting tighter and tighter and tighter, getting closer and closer to 1. Now to do that, I could stick this in the calculator and just do all these calculations, or I could jump to Maple and I can put this into Maple and very quickly evaluate this thing. So in Maple, what I'm going to do is I'm going to set up a function. I'm just going to call it s of t, and I'm going to make it equal to, what did we say? It was negative 16 t squared minus 100t. Whoops, I forgot to get off of the superscript. There we go. Minus 100t. Hit enter, and it's going to say, yeah, do I want to define a function? Yeah, that's what I want here. I want this to be a function. So now I have this function s of t. So what I'm going to do is I'm going to take two variables. I'm going to call it just a So A I'm going to make equal to 1. And then I'm going to set B equal to 2. And now I'm going to have Maple do a little bit of math for me. I'm going to tell it to take S of B, so that's S of 2, minus S of 1, and divide all of that by B minus A. So that's going to be 2 minus 1. Now when I do that, I get the wrong answer. And that's because looking at this, I can see this is supposed to be positive. My bad. So I'll hit enter again. Yes, it's a function. And now let's hit it here. And there's the 52 that we got earlier. Now, the nice thing about this is all I have to do now is take this B right here. It was a 2. Now, in the chart, I wanted it to be 1.5. So 1.5. Enter. And it's 60. So I can put 60 on my chart. Now, see, I wanted 1.1. So I'll make this 1.1. 66.4. And let's see, 1.001. And that's 67.984. So you can see this is getting closer and closer and closer to, gosh, I'm not sure. Is it 67.9 that I'm getting really close to? Or am I getting infinitely close to 67.98? Or could I just be getting infinitely close to 68? What I could do very quickly here is drop in another 0. It looks like it's going to approach 68. I'm going to put in another 0. See the difference now? I'm taking in the denominator, I'm taking 1.00001 minus 1. So I have this horizontal distance of only 0.00001. So I'm getting very, very, very close to 1. And then that's what I'm using for my denominator. And I'm taking the value of the vertical distance between S of B and S of 1. So that's getting very, very, very close to the same vertical distance. And that's what I'm getting every time. I'm getting closer and closer and closer to some value. Now it just jumped to 68. And it kind of leads me to believe that, at least within rounding, that the instantaneous velocity is probably going to go to 68. So just to fill this chart in quickly, we had 60. And then this was 66.4. And with 3 zeros, it was 67.9984. This is the whole idea behind the limit. What's the limit as this value of x approaches this value of x, as the distance between them becomes 0? What value vertically am I approaching? Well, actually, that part's not true. It's not which value vertically am I approaching. It's what's the average of the two different values am I approaching. That's the idea of the limit as I presented it here in this particular case. So, in a nutshell, that's a quick example of how limits are used. In this case, it would be to find the value of an instantaneous velocity based on average velocities. That average, as that limit on the x-axis or t-axis here, as this distance becomes 0, as we approach 1, as this value approaches 1, we're approaching the limit.